All right, we'll get started. So I'm not Saeed, I'm Steve Bates, I'm the CTO. This is work that we did at Eideticom. We are a startup working on computational storage using NVM Express. That is not something that is currently part of the NVMe standard, but the wonderful thing about standards is they evolve. And maybe NVMe and other standards will evolve to take advantage of computational storage. We think it's a very interesting idea, and we hope you do too. And in order to kind of justify why things like NVMe or SCSI or Fiber Channel might change to allow for computation on or near the storage, we kind of have to showcase some examples of getting benefit by doing something. So this is actually work that came out of a customer engagement. So I'll give you a little history on what the customer was looking for and kind of how we solved that. I can't name this customer, but they're quite a large data center customer. So that's pretty good. And we're continuing to work with them as they kind of evaluate and go pre-production into production and so forth. So kind of pretty neat to see, but we'll talk a little about that. Before I jump into that, most of you, I'm sure, in this room have heard of NVM Express. If you haven't, why on earth are you here? You're in the wrong conference. Please go away. It's a standard specification that was designed from the ground up for accessing non-volatile media. Originally for PCIe, now obviously with fabrics, we have multiple transports. You know, one of the things that was always interesting, I used to work for a pretty big SCSI shop for a while, and we were always like, is NVMe actually really better? And there are actually some reasons around why it is better, particularly around multi-queue and stuff like that. And now obviously it's very hard. Well, it's not hard, but you have to look around now to find a solid state drive that isn't PCIe-based anymore, NVMe-based, right? You can still get them for sure, and people are still using them, but it's getting harder and harder. It is designed to be high speed, high throughput, and pretty CPU efficient, and very importantly, designed for parallelism. One of the things about NVMe is it supports many hardware queues, much more than most people put on their controllers. And you can basically take those queues and map them to the multiple cores you have running on your processors, because Dinard scaling says we can't go to 8 gigahertz cores, so we end up having 2 4 gigahertz or 2 gigahertz. Or recently I had a system in my lab that had 256 cores. That was a bit painful, but we take advantage of all those cores with their different threads and issue I/O from all those cores against these drives. For us as a small startup, this next point was very important. We had a decision to make. We're going to do computational storage stuff. Do we call it Eideticom and write an Eideticom driver that's kind of shitty because we're not great at writing kernel code? And then do we go to the customers and say, hey, customers, I know you're using Ubuntu, but can you install this shitty out-of-tree driver that might not work with your particular backports and might cause a bug on your bare metal and bring down 10,000 of your servers? And then wonder why we sell absolutely none of them, right? So for us, it wasn't even a choice. We had to align with something that's already in upstream kernels. We're going after hyperscalers. We're going after data center customers. We can't provide shitty kernels on our website, right? We have to be working with inbox drivers. On top of that, the NVMe driver, I haven't done the math, but if you look at the hours devoted and the average salary of the person who's working on the NVMe driver, that driver is probably tens, if not $100 million worth of software development salary. So yeah, I'll use that. It's like, why wouldn't I, right? And I'll show you in a minute why it makes a lot of sense. So one of the other things, I talked about this yesterday, NVMe has standardized something called the controller memory buffer. It's basically a PCIe bar. And that's a piece of memory that can be used for DMAs. But in order to utilize that, we need the operating systems to support it. So we also have been working on something called the peer-to-peer DMA framework. I talked about that yesterday. If you're interested in learning more about that and where we are in terms of upstreaming, and the answer is hopefully very, very close now, you can come chat to me. All right. And the peer-to-peer transfer is there to reduce the load on the CPU system memory and to free up CPU time. Okay. So NVMe can be used as a high-speed platform for sharing accelerators. So we use NVMe today to talk to traditional NVMe SSDs from Intel or Samsung or Seagate or whoever. But we can introduce these new devices. Our product is just one example. There's other companies like NGD Systems and ScaleFlux, and some of the larger companies are starting to take a look at this. And these are also NVMe devices, but they don't have any storage. Some of them do. Ours do not. We don't store a damn thing. I spent a long time working for a company that makes SSD controllers. I spent 6 years of my life trying to get very fucking clever companies to get SSDs that work based on our controllers. And I went, there's no way I'm ever fucking doing a startup that talks to NAND ever again. Can I be more clear about that? So I think it's a great business, and I love SSDs, and that's great. But if I'm doing a small startup, I don't want to be an SSD. I want to be a computational engine. Why try and solve two hard problems at the same time? So these are these new accelerators, but they just happen to present to the OS as NVMe devices. So you take one of our cards and you plug it in your system. The class code is non-volatile memory, and the subclass code is NVM Express. And the driver that it binds to is the inbox NVMe driver, right? And then we go from there. So now I've got an interesting system, because now I've got high performance, low latency storage. This could be NAND. This could be something that's not NAND, which makes it AND. Boolean joke. It could be Optane, or even something like a SpinTorque or an Antero stuff. But the interface is NVMe. This could even be over fabrics. Right? This could be a high-performance networking device, RDMA or TCP/IP coming soon, or fiber channel, and then you could have your storage somewhere else. You can take it. I want to know who it is. Right? But now on top of my storage, I also have this accelerator compute. Right? And this could be doing a number of different things. I'm going to focus on compression in this talk. But we are working either ourselves in-house or with partners to put other interesting PCIe acceleration functions here. Artificial intelligence inference, right? Because our investors say we're worth 2 times more than we are if we'd say AI. Right? So, anything, and because we're moving to a world where things are more heterogeneous, right? AI is not best served on an instruction set architecture, or at least the ones we get from AMD and Intel. So if I'm running a lot of AI, we're already seeing a lot of servers where we have a lot of PCIe accelerators, right? They might be Google's TPU, or they might be an NVIDIA card, or they might be an FPGA card, right? And we're struggling to come up with good frameworks for how do we manage these accelerators? How do we tie them into applications? And one of the things people want to do also is they don't want stranded resources. So if I have a server that has 16 accelerators in it, and I don't need all 16, how do I let this server over here that needs 18 borrow the 2, right? And I talked a little about that yesterday morning with Sean, and we show you how NVMe can actually allow for that disaggregation, which for me is another great benefit for using NVMe. All right, so I'll dig into the specifics of our platform. Did I bring it? Where is it? Oh, I didn't bring it. That's very strange. Normally I have one with me, but I forgot it today, or somebody stole it. We call it NoLoad. And my mic fell off. We call it NoLoad. Bang, 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 bang. Sorry about that. So NoLoad stands for NVMe offload. And basically, it can present, in this case, FPGA accelerators. I mean, we could do an ASIC if we raised enough money and wanted to go through all that pain. But we're not quite going to do that just yet. So we deploy on FPGA, and there's other good reasons to use FPGAs because they can change their functionality over time. So that's something that we're doing. But we present, like I said, we present that computation, that FPGA resource as an NVMe endpoint. So we have an NVMe endpoint in there, and then we can basically use namespaces, which is an NVMe standard construct, to present the different accelerators in a way that the operating system can carve up and give to different applications, right? So in the same way, you can take a chunk of NAND and carve it into different namespaces and share that from behind a controller. We can take some amount of compute resources, chunk it up into namespaces, and give those to different applications that need them, right? It also allows us to have, one accelerator can be a compression engine, one can be an erasure coding for RAID or, Reed-Solomon calculations. It could be a artificial intelligence inference or training or something. But once that's tied in, we can use standard NVMe tooling to manage this device. So you can imagine if our customer is already on a path towards NVMe and they're writing management code, the fact that our accelerator presents as an NVMe device and can be managed with the same piece of software that they're managing the drives, that's a win, right? Because they don't have to write a different management stack for their accelerators. We can do things like enclosure management. We can do, we can follow all the rules around LEDs. We can come in the same form factors as as NVMe drives can. So we have a U.2 form factor who was, the hardware was actually from Nanotech. Alan, just wave, Jan. Alan, great partner on the hardware side. He builds the hardware. We put the bit file on that turns it into NoLoad, and everybody wins, right? But we can also deploy as an add-in card. We could deploy on something that has lots of FPGAs. We're not particularly fussy in terms of the physical deployment. We're more interested in the smarts that we enable on that platform. And then we have an API that sits in Userspace, and I'll show you some of that in a little bit, that uses the NVMe driver to access the hardware. So we still have the kernel in the path, which is great for isolation and security and high performance. But we basically then operate using a library in Userspace, and then we present an API that someone like yourselves could use to tie into your application. So you could do Ceph, acceleration, you could do something else, and we have the APIs to do that. So on that point, the software stack for us is very important. We do not change a line of code in the kernel space. Never touch kernel space if you want to be a successful small startup, because you will die under the workload, right? The great thing is, this driver is very well defined. One of the things I love about NVMe is they didn't do what IBTA is. They didn't define verbs somewhere up here in this wishy-washy software space. They said, your PCIe device will have fucking registers at this fucking offset that do exactly this. So, and then we still get quirks. I mean, we still have drives that don't all work quite the same way, but at least it's a lot better than RDMA, where you have to have a driver for different NICs for those particular NICs, right? So the same driver works for Intel drives as it does for us, as it does for Seagate, as it does for anyone else. And that's true for VMware and for Windows and for Linux, and do we really care about any other operating system after those three? Also, if you want to do things in Userspace using things like SPDK, we're supported there. We're just an NVMe device. Anything that works with NVMe works with us. It's really quite that simple. And then the APIs we provide are free and permissively licensed under the Apache licensing on a GitHub account. So if you're interested, you can go there right now and take a look at our code. And we provide some example applications that build on that API to actually do interesting things. All right. We have some customers who have asked us to do certain things in the kernel, and for them, we have made kernel modifications. So one of our customers is very big on ZFS, and it's public, right? It's Los Alamos National Labs. Great guys, great partners, really enjoying working with them. And they were like, well, we do RAID and compression in ZFS. Can we offload that to your device? Right? We can't do that in Userspace. ZFS is it has a user space, but it has a kernel space, and that's the one we were interested in. So we actually went and took a look. The compression part of ZFS already has support for accelerators. Intel's Quick Assist was added as a support device. It was literally 2 or 3 lines of code for us to tie in to that particular part of the stack. What's kind of interesting about that work is the way that we did it is we actually changed the driver so that when we advertised as an NVMe device, we said, oh, and if the NVMe device is an Eideticom device, don't register it as a disk. Register it as a special pointer that we can pass to the compression and RAID parts of ZFS, and you can use this in kernel. Right? And if we change the NVMe standard to standardize that, then we wouldn't have to make those changes out of tree. The NVMe standard itself could come up with a way of saying, hey, I'm a namespace type, I'm not a storage namespace, I'm a computational namespace, treat me differently. And we can actually have people submit patches to the Linux kernel. and the other operating systems in order to support anyone who wants to build NVMe devices that can do compute as well as or instead of storage. Right? And there was a birds of a feather last night within SNIA. We're kind of moving forward on discussions on exactly that kind of topic. I'm not going to say for sure, hand on heart, exactly what's going to happen, because I can't predict standards. I don't think anybody can. But it's going to be an interesting discussion. For those of you who are familiar with NVMe, you've probably used NVMe CLI. It's a free and online tool from Keith Bush at Intel. It's kind of one of the de facto tools for managing the drives in your system. So there's a command called NVMe list, which you have to run as root unless you've set up permissions on your disk devices. And you get a whole bunch of information about the namespaces in your system at the current time. You can see here we actually have 3 Intel drives, and then we have 4 namespaces associated with our Eideticom device. So it's pretty typical today that you get 1 namespace on a drive. Some other drives have namespace management, so they might have quite a few. But this device here actually has 4. Now, NVMe CLI allows for vendor-specific plugins. So Intel has a plugin, WD have a plugin, Seagate have a plugin. We have a plugin. Ours is EID. So when you do NVMe EID list, basically it only lists Eideticom devices, and it looks at the vendor-specific field of the namespace identifier to extract more information that's vendor-specific about that namespace. Right, and this is very standard. All the drive vendors do it. This is how you get things like firmware versions and all kinds of other wonderful stuff. What we use it for is to identify in a human-readable way what our different namespaces do from a computation point of view. So we have 1 RAM drive, which we use for test purposes, and we have 3 compression cores in this particular incarnation. If we burnt a different bit file, that list could be different. We could have Reed-Solomon, we could have SHA, we could have artificial intelligence, blah, blah, blah. Right, and maybe some of those names become standard. Yes? Because there's 4 here and there's 4 here. In this particular parsing, because you're not using the plugin, you have no idea about non-vendor specific stuff. You can only go to the standard defined fields, and this is basically our namespace name.
So if I look at the left-hand column, it says in1 through in4, and
yep.
in1 is then the Eideticom RAM driver. So
yep.
Is that the same as?
Yeah.
Okay.
Yeah, exactly. So this particular function call can't do anything vendor specific because you haven't called the plugin. This particular function call, because you're calling the Eideticom plugin, can look at vendor specific fields, and it understands how we've taken the vendor specific field, which is quite a big field, and carved it up into subsections that are useful. And then this prints it out in human readable form. So this particular version is a little older. Our current version actually dumps like the build time of the FPGA and the version number of the accelerator, so we can obviously keep track of versions and stuff. And interestingly, this works over fabrics as well. So if our FPGA was plugged into an NVMe over fabrics target that was then exposing the namespaces over Fibre Channel or TCP/IP or RDMA, you could extract the same information even if the accelerator is no longer direct attach, but it's connected over fabrics. Yes? What's that? Well, that's vendor specific. So one of my apps guys would know what it means. I have no fucking idea. Basically it means everything's working really well. Yeah, there's information in there, and obviously it just depends exactly. Yeah, it could be a date stamp. All right, so that's kind of the NoLoad. That's the product that we're bringing to market and going to sell for loads of money, and we'll be flying around in private jets this time next year, apparently, if you believe the hype. But on top of that, one of the things that we recognized as we were thinking about NVMe for acceleration was also the fact that PCIe-based servers are getting very, very fast, an awful lot of I/O. So you put in a couple of 100 or now even 200 gig Ethernet NICs, you put in a bunch of NVMe drives, you put in a bunch of graphic cards, you could easily get 50 or more gigabytes per second of sustained data movement around PCIe. And in the Linux, or in all major all operating systems today, the way that that works, if you move data between two PCIe endpoints, so I have an example here of a copy between two NVMe drives, the path today is DMA to system memory, and you might get last level cache, so it might not all go to DRAM, right? There's DDIO and other things that can happen. But the path is traditionally you allocate pages out of your main memory pool, typically DRAM. The DMA goes there, and then when it's done, you get a completion and you issue another IO to the other drive saying, hey, can you DMA this data into you, right? Now imagine I've got 200 drives and an RDMA NICs and graphics cards, and they're all doing different things. All of that data is going either over this interface or it's hitting the last level cache, right? That is a huge, huge problem. That either means one of two things. Either you need like 6 DDR channels just to get the bandwidth, in which case you're paying for a processor whose instruction cycles you may not even need or want, but you just need memory channels, right? Or you're in a hyperconverged environment and you do need those Xeon instruction cycles because they're running VMs and applications and containers and Kubernetes. And in which case, they are fighting for the same DRAM that the DMA traffic is using. So there's a quality of service, there's a contention issue. So either one of those is bad, right? So what peer-to-peer DMAs do is they allow you optionally to say, hey, rather than allocate my DMA buffers from here, can I allocate them from memory that's on the PCIe bus already? That's what we're enabling with the peer-to-peer DMA framework, okay? And the most classic, the most relevant example of a device with memory already on it, on a PCIe endpoint, that's done in a standards-based way is the NVMe controller memory buffer. Right, so other devices have memory. Graphics cards obviously have a ton of memory on them, but they don't necessarily expose it, and they certainly don't do it in a standards-based way. Right. So now what we can do is the DMA can basically be this DMA here, and then this becomes an internal ingestion, an internal DMA. It doesn't even go back out on the PCIe device. Right? We have to make sure, there's all kinds of issues we have to worry about. We can get into certain PCIe topologies have problems with this. Access control services is very, very scary. Don't do this in hypervised environment. Don't do this from a VM, please, right now. We'll get there, but right now, this is kind of a bare metal only thing.
Before you go to the next slide, so that legacy path, there could be legit reasons that you want to use that.
Yep.
You want to change the data or forward it on.
Exactly, yeah.
So is anybody thinking about being able to break up a peer-to-peer transfer? Say, look, at this offset, these number of bytes, you want it to go up to the DRAM complex?
Yeah. Well,
continue.
so there's a couple of ways you can do it right now. I mean, right now, if you're a Userspace process, the upstream patches don't actually expose peer-to-peer in any way to Userspace yet, but we have a hack that does that. That's a driver for P2P mem. And what you can do in your application is you can allocate buffers in both normal memory and peer-to-peer memory, and you can make decisions as the application writer on which buffers to use at which given point in time, given who's talking to who. So, yeah, exactly. So SPDK is a good example of that. SPDK, you can either call from the CMB to allocate memory, or you can call from something else. And you can make decisions based on your understanding of the PCIe topology and what you're doing. Yeah, in the kernel, we will have to have discussions around that. We will have the discussions around Userspace APIs that make sense.
But that's an example
Yeah.
of what you want to push upstream.
Yeah, I mean, I mean, all the things that we're pushing upstream right now are typically, if peer-to-peer doesn't work, fall back to the legacy path. Like, we're not saying break the DMA, right? I mean, people may want to break the DMA if it doesn't work, but that's a decision for down the road.
So you're kind of making use of the stock drive or making the most of it, but it's not optimal by any sense.
Not yet. No, not at all. No, and I think there's a lot to be learned. I think once we get upstream, that's basically the green light for a lot of people to start playing with it, and we're going to get a lot of input and discussion around how best do we use this, how best do we use it in the kernel, how best do we use it from Userspace, what are some of the things we might need to look at to make those judgments calls. Yes.
A quick question, a longer question. You have CMB and bar. What's bar?
So a bar is a base address register that's a PCIe construct, PCI construct, and basically it's memory mappable I/O memory.
So the other question I have is, in your right-hand drawing, you kind of have this magic line that goes through the CPU. It doesn't say where. Oh, it does show a CMB. Is there a CMB in the NVMe side?
No. So you only need, you actually only need one device to have a CMB to start playing. And it could even be that the devices you're copying between, neither of them have a CMB, but another device does. In which case you would have a green line to here, and then you would have another green line into the other device. So you can do DMA, peer-to-peer DMAs between two PCIe endpoints, but actually use a third PCIe endpoint as the donator of the peer-to-peer memory.
So are CMBs in some sense faster than bars? Or
No. A CMB is just an NVMe definition on top of a bar. Physically, they are the same. The CMB is just a way, an NVMe standard way of allowing the operating system or informing the operating system that part of this bar has certain properties that may be desirable for the operating system to use. All right. But from a functional point of view, it's just a bar or a part of a bar. Yes.
So for the peer-to-peer to work, you need to have the destination actual physical address.
Correct.
Right?
And that's part of what a peer-to-peer framework does.
So it has to go to the CPU's VTB table, right?
Only if the IOMMU is on. And even then, it doesn't necessarily, because you may have translated it before you passed it down. Yeah. But typically we assume the IOMMU is off. That's why I'm saying don't do this in virtualized environments today, because we haven't really got there yet. I think we will, but it's going to take a bit of work. And then you also obviously want to disable access control services on the path between these endpoints, right? So that the DMA can go.
SSDA in this picture has the address for the CMB.
Correct. That's what you give it.
So it has to
Yeah.
work with the IOMMU to get the real addresses.
It has to work either that or with the hypervisor. It doesn't actually physically go to the IOMMU per se, or it doesn't have to. There's a couple of different ways of doing it. But right now, like I said, we are advising people who want to do peer-to-peer to do it on bare metal and preferably just disable the IOMMU. Right. That's what we're advising as people ramp up. We are starting to have discussions at the highest level around, okay, now that it looks like we're getting the bare metal stuff upstream, how do we start doing things in more virtualized environments where an IOMMU must be on and we have access control services. And for example, we might pass through two virtual functions, right? So this is a device. It could have SRIOV. It could have some virtual functions, and we pass a VF of this to a VM, and we pass a VF of this to a VM, the same VM, right? How do they do peer-to-peer? Can they? Should they? Should we just say never do that? And then even more interestingly, or maybe not, we pass a VF of this to one VM, we pass a VF of this to a different VM, and we want to do a peer-to-peer between the two. That is starting to terrify me, and I'm not even a hypervisor person. Right? So yeah, it's a good question. We don't have all the answers yet. The great thing about open source software is it evolves, right? Yes?
How does it work with the multi-socket CPU system if you have?
Yeah.
Will this work?
So it's a good question, yeah. So what happens in a multi-socket environment? The reality is that right now the code that's upstream will recognize that and it won't do the DMA. It will fall back to using system memory because it's a really stupid idea. We do have some config-fs stuff that you can use to override that. If you know your system is good and you want to do that, then technically it works, right? The performance may vary, and you're certainly going to load up your socket-to-socket bus with traffic. So you can do it, and it probably will work, but it might not. All right, so peer-to-peer DMAs, the kind of customers we're working with on this right now are very much people who understand the environment in which they're doing this and have a good sense of the PCIe topology and are making well-informed decisions around static systems that are not going to be changing all the time, right? Over time, there may be other people who want to use it, but that's not, we're not there yet. And if somebody's so unaware of their system, that they try to do peer-to-peer across the socket, they probably deserve everything they get, right? Because they weren't making good decisions. Right? This is not something that's going to be on by default. You will have to go and do a bit of work as a systems architect to actually turn this on, even in the operating system. Okay. So we took those two different pieces together and combined them for a customer. So the customer was basically deploying they were actually on an Intel-based system, but we ended up doing a demo with AMD, and I'll talk about why that is in a minute. But they were asking us to do compression on data that they had on some NVMe drives. And they wanted to get the compressed data onto another set of NVMe drives, and then they were actually buffering it out the back to a capacity storage tier. But they actually wanted this path to be done in a peer-to-peer fashion so that they weren't impacting the load store of the applications that were running on the processor. Right. So what we did is basically said, we took our lib NoLoad, we used the inbox NVMe driver, and we wrote an application that basically did peer-to-peer data movement with compression as part of that movement, using the compression engines in the NoLoad to do that. So the way that that works out is basically you end up doing an NVMe read command to the input drive, right? And this works through VFS. So you can have a file system on here. We had ext4. And basically you can start issuing NVMe IO against this drive. And as the gentleman mentioned earlier, the pointers, the SGLs or the PRPs in those NVMe commands point somewhere in our controller memory buffer. So this guy starts issuing mem-write TLPs. And hopefully they get routed by PCIe. It's certainly in the AMD system, which is good peer-to-peer characteristics between its root ports. We were seeing very good performance here. So the mem-write TLPs would come in, and we'd put them in our CMB. And then when this guy had issued his last mem-write for the DMA, he raises an MSIX interrupt. The NVMe driver gets recall backed. It handles the completion. At that point, the application knows that that I/O has completed successfully, and data is on our CMB. Right? What it then actually did is it actually sent us a command to actually process that data via the compression namespaces and put the result back in the CMB at a different location. So that's basically another NVMe command, basically saying, hey, take the data, put it there, and then put it back in a different place in the CMB. And obviously, there's multiple threads doing this simultaneously to different parts of the CMB. So we've allocated the CMB in different chunk sizes to different threads, so nobody can sit on top of each other, and nobody can DMA over the top of others. And we use the NVMe completions to know when everything's done, and run that through P threads in a P thread safe way. And then once the data is compressed, we basically issue a completion and raise an interrupt and tell the application, hey, we've done the compression, and by the way, the data is where you asked us to put it somewhere else in our CMB. And then what it can do is the drive can issue NVMe write commands to the output drive, pointing again to our CMB to the compressed data, and the compressed data gets written to the ext4 file system on the output. All right. So given the FPGA that we had here, we can only get 3 compression cores on that, and we can do about 1 and a bit gigabyte per second of input data compression per core. So if we had a bigger FPGA, we could go more. Also, they wanted U.2 because they were deploying in this kind of server, so U.2 is a good form factor, in which case you have a PCIe Gen 3x4 limitation until we get Gen 4 processors, right, which are starting to appear. But AMD are on a path to Gen 4. I think Intel are on a path to Gen 5 at this point, but I don't know. I haven't seen their roadmaps. Yeah. Question?
So you said you fit 3 instances, 3 GZIP instances into that particular FPGA.
Yeah.
Can you say whether it was LUT limited or block RAM limited?
That's a good question. I think it was actually reasonably balanced. And I think it was really more just closing place and route, given that we were at like 75% resource utilization.
And was each instance encode anticode, or one or the other?
That's a good question. So in this particular one I showed you, they were all encode, and the customer's doing the decompression in software, just because it's much less expensive. But we have other customers who want us to do compression, but they're more concerned about data corruption. So we actually put decompression in. So we basically do a SHA on the input data, and then we compress the data, and then we decompress that data, generate a SHA, and make sure the SHA match.
And there's no dedupe in here, right?
That particular one does not, but we do have dedupe engines. Yeah. Yeah. Yes.
When you're basically have CMBs with pointers before and after compression within the CMB, are there two different PCIe bars?
No, just one bar. So the peer-to-peer DMA framework is responsible for allocating memory out of that bar. And it's a very safe, well-tested kernel allocator. So it's not going to give 2 pages to 2 different, the same page to 2 different processes. So you're not going to end up with 2 devices trying to DMA over the top of each other. And then the driver, when you're done with the memory, when you free it, it goes back to the allocator. And the idea is, and obviously the allocator can fail. If you've allocated all the memory and somebody comes and says, can I have some more pages, please? They're going to get a minus E no mem, right? And they'll have to fall back. The application has to handle that error somehow. Yes.
So your comment about decompression being faster in software,
Yeah.
is it because your FPGA was too small to have more decryption engines in the FPGA?
No, so deflate is a pretty simple algorithm, right? So it's just not very computationally intensive on any processor. So the compression algorithm, because of the static Huffman tape or dynamic Huffman in this case, and some of the other things, like libz in particular, is quite onerous on something like an x86 64 instruction set. So, thank you. So, it made sense to target that. And this particular customer did want libz compatibility. There are other compression algorithms that get reasonably good compression without being as taxing on the processor. So LZ, for example. But they wanted ZLIB. Right? And there's obviously, everybody has their own favorite version of compression at any given time of any given day. In our particular product, we ship, the U.2 has 8 gigabytes of DRAM on it. We typically expose 512 as a CMB, but only for the reason that it's a nice round number of 2. We can make it bigger or smaller, and yeah, we do. 512 is a lot.
Can I make sure I heard that correctly? You allocate 512 megabytes for a C.
For the CMB, yeah. Yeah, I don't think in this particular application it even used a quarter of that amount. Like I think, 16 megabytes would have been. Think of it as a delay bandwidth product thing. It's basically your buffer needs to be your throughput multiplied by the time to write to the output. So it's just a delay bandwidth. Yeah. Yeah. So that's a good question. Yeah, so what about scaling? So there's a couple of things that happen. So one of them is, I think if anyone's going to XDF next week, we basically are doing this demo scaled up there. So basically more NVMe drives, more NoLoads, and more output drives. And we're basically showing that if you do that correctly, you get linear scaling in performance. Because you're using peer-to-peer, there's no bottleneck anymore. In theory, because everything's doing DMA, I can partition my system in the PCIe domain in a way that I can just basically stamp out this block as many times as I like, this block being input drives, NoLoad, and output drives, and my performance will just continue to scale ad infinitum.
Are all those devices on the same PCIe bus? Because at some point, if they were, that would become a bottleneck.
What's that? Are they on this? Well,
yeah, the SSDs and the NoLoad accelerators.
So in this particular system, and it'd be good to draw a diagram of this, but basically everything is connected to, every single device on its own is connected to a single root port on the AMD EPYC. And the AMD EPYC was designed to have great peer-to-peer performance between the root ports, especially when those root ports reside on the same socket. But even across sockets, they claim good peer-to-peer performance. As long as my atomic unit, as long as my atomic building block connects to root ports that are always on the same die, there is no contention between this atomic unit talking to these root ports and this atomic unit talking to those root ports. right? Because they don't even need to talk to each other. So that, in theory, could scale ad infinitum, right?
Make sure that the inbox driver uses the CMD address instead of going to the regular.
That's what the peer-to-peer DMA framework that we're upstreaming into the Linux kernel does. So,
What I mean is, how does the inbox driver knows how to use the CMD?
so go take a look at the patches, and that will definitively tell you exactly how that is done. Yeah. Basically, if you go take a look at our patches to the NVMe PCI.c file, you'll see, well, it's not even in there. In the block layer, we basically have the ability to submit a scatter-gather list, which is backed in part by peer-to-peer pages. The NVMe driver has no idea. It has no idea it's doing a peer-to-peer DMA, because all you're doing is you're asking a DMA master to start issuing some memread or memwrite TLPs. That DMA master has no need, nor should it know whether it's DMA in system memory or somewhere else in the system. That's not its job to know that. In fact, we don't trust these things one bit. That's why we have ACS in the first place, is because we don't trust the endpoints to do shit, right? We tell them what to do. Right? So the NVMe driver doesn't really have to be peer-to-peer aware per se. It just needs to pass through the PRPs that are allocated from the PRP allocator, which is done at the block layer. Yes?
So when you've got the data in the CMB and you want to run the compression command on it, so is there a driver down there that does that? Do you send a command, or is that like a hardware or firmware?
Yeah, it's actually RTL, and we're not going to even get to those slides, but in the deck that will go online, we actually have some numbers in terms of the RTL that we wrote to do the compression engine. So you're right, it could have been a software compression engine.
My follow-on was more, did you consider using the quickest device to do as a compression engine?
To use which device?
The Intel quickest device.
Oh, yes. So actually the full version, which will go online, compares what we're doing to the Quick Assist in a bit more detail. The problem with the Quick Assist is, A, this is an AMD EPYC, so it doesn't have a Quick Assist. And B, normally the Quick Assist is on the PCH device, which is DMI connected, and isn't necessarily a peer in the PCIe subsystem. So if you want to do peer-to-peer with a Quick Assist, it's not going to work, because the peer-to-peer is not peer-to-peer. It's because the Quick Assist is hanging off the PCH, and normally your high-performance PCIe is hanging off the processor core sockets themselves, right? Now, you can also go buy a Quick Assist like as a PCIe card, and that could certainly have replaced us, but that just means Intel make money and I don't. So I'm not a big fan of that particular model. Well, there you go. So we'll do that. We'll just stop my company and we'll sell more Quick Assists because I'll do anything to make Intel happy. Yeah, exactly. Yeah, and we do have some performance numbers that compare to the Intel Quick Assist, but we're not going to have anything like enough time to do that. Right. So yeah, we're not going to get into that. Let's not bother. So if if you're really interested in the minutia of the RTL we wrote to do the compression, then feel free to come to me. I can't even answer the question because Saeed's the best person to talk about the specifics of our compression core. We did do some comparisons to Quick Assist and some of the other hardware-based compression research that's been done, and we feel like we have a pretty good compression core in terms of compression ratio and also throughput on standards-based corpuses like Calgary Corpus and some of the other ones. But for me, the story is not just do we have the best compression in the world. For me, it's much more, do we have a framework that's pretty awesome? Compression is one example of what I put in here, but imagine it's pattern matching or image processing or security or data recognition or deduplication or whatever. Part of me doesn't even care what service is behind here. And part of our business model is actually now, we're starting to work with some partners who want to use us as the platform, but push their own accelerators, not developed by us, but push their own accelerators that are maybe based on SDXL and map them in as NoLoad namespaces. Right? And in which case we become essentially a platform on which other people can innovate. Right?
Do you have an abstraction?
Yeah, so our abstraction is very similar to SDXL. So if somebody has an accelerator that's already SDXL, so anyone who's doing Amazon F1 work, for example, that's SDXL. They can take that accelerator and they can pretty seamlessly, without us really having to look at any of your proprietary code, and we can turn that through a wrapper process into something, assuming it fits in the FPGA, would be deployable behind this NVMe front end. Right? So that's kind of where we're going. So I'm sorry I didn't get it to all the compression stuff, but all this other stuff. Yes?
What is the ratio of scalability when using one? Or if you have multiple drives
Yep.
on a server, how many drives can use your NoLoad FPGA?
Yeah, so the question there was around scalability. In terms of how many drives obviously we have some pretty hard limits here, right? So we have a PCIe Gen 3, well, we have a PCIe Gen 4x4 interface here, but the servers in which we deploy today are Gen 3, so we don't get the Gen 4 benefit, but there is a throughput thing there. The actual throughput that we can hit is always a function of the size of the FPGA. So some of our customers, while they like this form factor, don't necessarily like this FPGA. And they can work with people like Alan to see if they can fit a bigger FPGA here or a smaller one, or redesign their own U.2 form factor. Right? So that's always going to be a function. There is a DDR bandwidth issue inside here, right? You don't get that for free, but there's certain tricks you can play around caching and on-chip memory that can come to bear there. But the other thing is, once you've got something that works, and let's say this is working at 3 gigabytes per second, if I can just replete it, if I can just tile it over here, I get 6 gigabytes. If I can tile it again, I get 9. If I tile it again, there's no interdependencies between these units. The only final interdependency would be, would be if my processors couldn't issue any more I/O, right? But that's an awful lot of IOPS. That would be really the main limitation that would come into play. All right, thanks for your time. We're getting kicked out. Birds of a feather tonight on NVMe.